Welcome everyone. Today we'll explore about destructive testing or DT methods for pipeline integrity. Techniques to assess and ensure pipeline safety. What is destructive testing and its importance? Destructive testing or DT refers to a category of testing methods where the material or component under examination is subjected to conditions that ultimately lead to its failure. This approach is essential for understanding the mechanical properties, structural integrity, and performance limits of pipeline materials. Unlike non-destructive testing or NDT, which preserves the test specimen, DT provides direct insights into material behavior under stress, impact, and other extreme conditions. For pipelines, DT is critical because these structures operate under high pressure and harsh environments, making it vital to ensure they meet safety and reliability standards. DT helps engineers determine tensile strength, fracture toughness, hardness, and impact resistance, which are key factors in preventing catastrophic failures. By sacrificing a sample, DT allows for precise measurement of properties that cannot be accurately assessed through non-invasive methods. This knowledge informs material selection, welding quality, and compliance with industry standards such as ASME, ASTM, and API. Ultimately, DT contributes to pipeline integrity management by identifying weaknesses before they lead to operational hazards. Key concepts and challenges in pipeline integrity. Pipeline integrity refers to the ability of a pipeline system to operate safely and efficiently throughout its lifecycle. It encompasses structural soundness, resistance to environmental factors, and compliance with regulatory standards. Maintaining integrity is challenging due to factors such as corrosion, material fatigue, welding defects, and operational stresses. Pipelines often transport hazardous substances under high pressure, making failure prevention critical for environmental safety and economic stability. Integrity management programs rely on both destructive and non-destructive testing to assess material properties and detect flaws. DT plays a vital role in validating design assumptions, ensuring weld quality, and confirming that materials meet specified mechanical properties. Common challenges include balancing cost with safety, managing aging infrastructure, and adapting to evolving standards. By integrating DT results into predictive models, operators can anticipate potential failures and implement preventive measures. This proactive approach minimizes downtime, reduces repair costs, and enhances public trust in pipeline systems. Why DT is still relevant: comparison of DT and NDT. While non-destructive testing or NDT methods are widely used for in-service inspections, destructive testing remains indispensable for material qualification and research. NDT techniques such as ultrasonic testing and radiography allow for flaw detection without damaging the component, making them ideal for operational pipelines. However, NDT cannot provide certain critical data, such as exact tensile strength, fracture toughness, or ductility, which are essential for design validation and material certification. DT offers direct measurement of these properties by pushing materials to their failure point under controlled conditions. This data is crucial for establishing safety margins, selecting appropriate materials, and verifying compliance with standards. DT is particularly relevant during pipeline construction, welding procedure qualification, and failure analysis. By complementing NDT, DT ensures a comprehensive understanding of material behavior, enabling engineers to design pipelines that withstand operational stresses and environmental challenges. Overview of destructive testing or DT techniques. Destructive testing methods for pipeline integrity include tensile testing, impact testing or CHARPI, hardness testing, fracture toughness testing, bend testing, and metallurgical examinations. Tensile testing measures the material's ability to withstand pulling forces, providing data on yield strength and ultimate tensile strength. Impact testing evaluates toughness by determining how much energy a material can absorb before fracturing, which is critical for pipelines exposed to dynamic loads. Hardness testing assesses resistance to indentation, offering insights into wear resistance and material uniformity. Fracture toughness testing determines a material's ability to resist crack propagation, essential for preventing catastrophic failures. Bend testing checks ductility and weld quality by bending samples to specific angles. Macro and micro examinations reveal internal structures and defects, aiding in quality control and failure analysis. Each method serves a unique purpose, and together they provide a comprehensive picture of pipeline material performance under various conditions. Tensile and impact testing, hardness and fracture toughness testing. Tensile testing involves applying a controlled pulling force to a specimen until it fractures. This test provides critical data such as yield strength, ultimate tensile strength, and elongation, which indicate how a pipeline material will perform under internal pressure. The setup includes a universal testing machine equipped with grips to hold the sample and sensors to record force and elongation. Impact testing, commonly performed using the Charpy method, measures the energy absorbed by a material during fracture at high speed. This test is vital for assessing toughness, especially in cold environments where brittle failure is a concern. The Charpy test uses a pendulum to strike a notched specimen, and the energy absorbed is recorded. Both tests are fundamental for pipeline integrity because they reveal how materials behave under static and dynamic loads, ensuring that pipelines can withstand operational stresses without unexpected failure. Hardness testing determines a material's resistance to deformation, which correlates with strength and wear resistance. Common methods include Brinell, Rockwell, and Vickers tests, each using different indenters and loads. For pipelines, hardness testing ensures uniformity across welds and base material, preventing weak points. Fracture toughness testing evaluates a material's ability to resist crack growth under stress, which is critical for pipelines operating under fluctuating pressures. This test involves introducing a pre-crack in a specimen and applying controlled loads until failure occurs. The resulting data helps engineers predict how cracks will propagate in real-world conditions, guiding maintenance and design decisions. Together, these tests provide insights into material durability and reliability, forming a cornerstone of pipeline integrity management. Standards and precautions, sample preparation and safety. Proper sample preparation is essential for accurate destructive testing results. Standards such as ASTM and ASME specify dimensions, surface finish, and notch details for specimens used in tensile, impact, and fracture toughness tests. Samples must be free from defects unrelated to the test to avoid skewed results. Safety is paramount during DT because tests involve high forces, sharp fractures, and heavy equipment. Operators should wear protective gear, follow machine operating procedures, and ensure secure sample mounting. Additionally, disposal of tested samples should comply with environmental regulations. Adhering to these standards and precautions not only ensures reliable data but also protects personnel and equipment during testing operations. Industry Standards and Compliance, ASME, ASTM, and API Guidelines. Destructive testing for pipelines is governed by standards from organizations such as ASME, ASTM, and API. ASTM provides detailed procedures for tensile, impact, hardness, and fracture toughness tests, ensuring consistency and reliability. ASME standards focus on material specifications and welding qualifications, while API guidelines address pipeline design and integrity management. Compliance with these standards is mandatory for pipeline operators to meet regulatory requirements and maintain safety. These guidelines also facilitate global uniformity, enabling manufacturers and operators to adhere to best practices regardless of location. Understanding and applying these standards ensures that DT results are valid and actionable, supporting informed decisions in pipeline construction and maintenance. Advantages and limitations of destructive testing. Destructive testing offers several advantages, including precise measurement of mechanical properties, validation of material performance, and identification of weaknesses before deployment. It provides data that cannot be obtained through non-destructive methods, making it indispensable for design and quality assurance. However, DT has limitations such as the need to sacrifice samples, which can be costly and time-consuming. It is not suitable for in-service pipelines, restricting its use to construction and research phases. Additionally, DT requires specialized equipment and trained personnel, adding to operational costs. Despite these drawbacks, the benefits of accurate and comprehensive material characterization often outweigh the limitations, especially in critical infrastructure like pipelines. Pipeline failure analysis and emerging techniques. A notable case study involves a pipeline failure due to brittle fracture in a cold region. Post-failure analysis using DT revealed inadequate impact toughness, highlighting the importance of Charpy testing during material selection. Such incidents underscore the role of DT in preventing catastrophic failures. Looking ahead, advancements in DT include automated testing systems, integration with digital twins, and hybrid approaches combining DT and NDT data for predictive analytics. These innovations aim to enhance accuracy, reduce costs, and improve safety. As pipelines become more complex and operate under extreme conditions, DT will continue to evolve, ensuring robust integrity management for critical infrastructure. Recap and importance of destructive testing or DT in pipeline integrity. Destructive testing methods are essential for ensuring pipeline integrity by providing accurate data on material properties and performance limits. Techniques such as tensile, impact, hardness, and fracture toughness testing enable engineers to design and maintain pipelines that withstand operational stresses. While DT involves sacrificing samples and incurs costs, its benefits in safety, reliability, and compliance far outweigh these drawbacks. By adhering to industry standards and integrating DT results into integrity management programs, operators can prevent failures, optimize maintenance, and safeguard public and environmental health. As technology advances, DT will remain a cornerstone of pipeline safety and performance assurance.